Thank you. I need to put a checklist up of my computer to make sure I check that stuff. But yeah, so we're looking at reaction coordinate diagrams, and we're plotting energy as a function of what's called the reaction coordinate. The reaction coordinate is sort of where you are in the reaction. So if you think of the reactant, if you think of the reaction as being products and reactants, I'll use the whatever this reaction is from the GChem website. Is that a legit reaction? They're missing some charges. But if you think of a reaction starting out as reactants, let's actually just use something generic. So like, let's say we're looking at a generic reaction. That's just like A plus B goes to C. So C is our product, and A and B are our reactants. We have these two states that we look at thermodynamically. The initial state, which is the reactants, and then the final state of this, which are the products. And the reaction coordinate sort of describes, like as we travel this way along the reaction coordinate diagram, so we're traveling along the horizon down here, we're traveling forward towards these products over here. So if you think about it in terms of something that's easier to, like more familiar, like if you're throwing a ball or something and we're trying to kind of plot that as a function of like gravitational potential energy in position instead of energy and reaction coordinate, this would be the starting position of the ball, and then like this would be the final position of the ball down here. So if I take a ball and I throw it, it starts out with a gravitation, whatever its potential energy is up here where it's really high, and then in the final state its potential energy is lower because it's dropped down. In the path along here would describe how the ball is thrown. So, like, do I throw it really high and it comes down? Like if you're throwing a football, do I throw it like straight across like that? And that's true for a chemical reaction too. That's kind of what we're looking at. So we're kind of looking at the initial state of the chemicals and the final state. And then we're saying, what happens along that path there? How did the chemicals go, the reactants go from being reactants A and B to C. And so as I move along here, I'm sort of changing energy until I get over here to the products. And so this part of the curve this green part of the curve, that sort of describes the kinetics of the chemical reaction. Because it's the path. That's what kinetics are concerned with. Whereas the other parts of the curve, these flat parts that I've drawn here are not really curves. This is what describes the thermodynamics. When we talk about delta G, we're talking about the difference in energy between this and this. When we talk about kinetics, how fast is it going, we're talking about this path that it takes here. And so it's really similar to like a map or something, like if you're trying to trace out how long it's going to take for you to get between 2 points, this is, you can imagine it might look something like this. It's like, okay, well, the distance that I'm traveling is going to be important for that, not just where I start and where I end up. But yeah, so A and B, these are, starting material, and then we have our products over here. And then this point at the top here is important. So at the inflection point, up here is important. So like at the top up here, we call this the transition state. And the transition state for the reaction, it's kind of the point of no return. So this would be, let's say that you have A and B, and in order for A and B to go to C, so we have this chemical reaction, that they have to come in and like interact in some way. So it's like, let's say that C is actually like it's A and B and they form a bond together or something. I don't know. Actually, yeah, let's I'm going to change C just because I think this maybe will make it clear what I'm trying to say. Let's say that A and B form a bond like this. And that's our product, is just the formation of a bond between A and B. A and B are not real atoms, they're just variables or whatever. But so along here, you start out with A and B and they're just kind of floating around and they're individual molecules in solution. And then they bump into each other. And if they bump into each other in the right orientation and at the right speed, they'll start to interact really strongly and come up into what's in this transition state here, which is a very high energy state that is somewhere in between the reactants and the products. So you haven't really formed the bond between A and B. You just sort of have this really high energy state. And then when the bond actually does start to form, the energy of this starts to drop down until it actually becomes the products over here. So it's like if you're, imagine this again, if we kind of use this physical analogy of like a ball or something, if I have a ball here, right, and I'm trying to roll it up the hill, when it gets to the top right here, that's its energy is the very highest it's going to be. It's the highest potential energy it's going to have. And then as it gets to the other side, it's going to travel down and its energy is going to get much lower. So this is the highest energy that you're going to have. And it's the kind of this place in the reaction coordinate diagram where you're kind of like, you're not really A, you're not really B, you're sort of in between, you're in between those two things. Like it's sort of like I have this partial bond formed here. So there's a transition state is this fleeting kind of thing. It doesn't really exist. You can't isolate it. It doesn't exist for any kind of meaningful length of time. But we have, when we're kind of looking at the diagram here, this distance here, let me use a different color actually. So we're at the reactants. If we come up here and draw another parallel line right there, there's a difference in energy between the reactants and the transition state. And this difference in energy is what we call the activation energy. And that analogy to kind of rolling a ball over a hill or something is a good one. If you want to take a ball and push it over a hill, right, that's going to take a certain amount of work or energy. And you could calculate what that is. You know, like if you're like, okay, I'm going to try and move this over the hill. I need to get it at exactly to this point. And then it kind of takes over. The process just becomes spontaneous at that point. It just goes, boop. It's happy to go over down the other side without any additional energy. But I have to get it up to this point. So, you know, I got to get some friends. Let's say I'm lifting like a big boulder. We got to push it all the way to the top. And then when we get there, we can let it roll down the other side. But the part where I have to put energy into the system, if I am pushing a boulder uphill, you know, if I wanted to calculate exactly how much that is, it's the energy required to get it from here, the bottom of the hill, to this apex at the top of the hill. And that's the same thing with these molecules. It's like, well, if I want to get A and B to actually form a bond, I have to push them up to the top of this hill. And so how do I describe that energetically? I just describe it as the difference in energy between the top of the hill and the bottom of the hill. And we call that the activation energy. You analyze a trough the same way. Yeah, you analyze a trough the same way. I mean, you can think of this bottom here. You know, I've drawn them as lines. You can think of this bottom here as a trough, really. You know, it's got sort of a minima down here. But for a reaction coordinate diagram or whatever, you always have a barrier that you're going over. You know, you might have multiple of these barriers, and we can look at some of those. But if you had no barrier here, for example, then the reaction would have, yeah, actually this kind of ties into a nice, an important kind of part here, that the height of this barrier, the sort of the magnitude of the activation energy is, it tells you what the rate is in a sense. So I don't know if this is like precisely true from a physical chemist perspective, but it's a perfectly fine way to think about things. The higher the activation energy, so let me give you the abbreviated. So activation energy we abbreviate as E sub A. But the higher E sub A is, the activation energy, the slower the rate. So that's sort of the relationship to what we've been talking about with the rate, is that, if it should make sense, again, if we just keep using this analogy of a mountain, if I'm trying to get between this point and this point, and there's a hill to go over that's really short, like let's just say the one that I have drawn. If I have to get over this hill, that's going to take a certain amount of time. If this hill is higher though, like let's say it extends all the way up to here and I have to walk over it, it's naturally going to take me a lot more time to walk over this giant hill than this short hill. And so that's sort of the relationship that you can kind of tie to in your brain between the activation energy and the rate of the reaction, is that the lower this barrier is, the lower the barrier is to get to the transition state, the faster the reaction is going to go. Let's see if there's anything else. So yeah, I guess it's like the larger E sub A is, that I'm trying to remember all of what we kind of work into the modules here, but it's related to the rate of the reaction. It's related to the rate constant. So yeah, this stuff's related to K. Let's look at another one, like something that has multiple things, and that'll make that clearer. So let's say that we're going between so when we looked at reaction mechanisms, we realized that this way that we're looking at things, I'm trying to think of a reaction that happens in 2 steps. We realized that the way that we kind of have been writing things, where you just describe the overall, I know a good one. Where we've been describing the overall reaction as, let's say we're looking at a reaction like this. Let me change this so it doesn't look as confusing. Let's just call this water. So we'll write out, the overall reaction, and we draw it like this. But what we realize is that there's actually steps that are happening along the way here. It doesn't actually happen this way. This is just sort of the net result of adding the reactant and the product. If we want to look at the actual mechanism here, oh, I missed it. Sorry. Just missing a carbon atom there. There we go. So yeah, so the actual reaction mechanism takes place differently in these sequential steps here. So it's not like I put this in, and they magically become this. There's a sequential process that has to happen in order for the reaction to go. And so in the first step, we form whatever these 2 different things. It doesn't really matter what the reaction is. And then we have another step. That might look something like this. So step one, step two. And this would be the slow step. It's going to be crammed over here. Let me put it on the other side. This first step would be the slow step, and the second step would be really fast. Should I draw it that way? Let's put actually a third step in. So I'm trying to keep things simple and not make like this actually becomes this. The actual identity of these things, right, is I know they look a little bit obnoxious, probably. You know, it's not super important. Like if you're missing a 3 or something on there, missing a carbon atom, it's not going to change the overall outcome here. I just want to use a real chemical reaction so that I don't know, don't run into, sometimes when I just make stuff up, I kind of paint it into a corner with something where it's like doesn't quite make sense. So since I know this is a real reaction, everything will line up. So here's our overall reaction up here, right? And these are our fundamental steps down here. Step one, step two, step three. And so step one is our rate limiting step, et cetera, et cetera. If we look at a reaction diagram here, if we try to draw a reaction diagram for this, the number of steps that we have over here will correspond to the number of peaks that we will see in our reaction coordinate diagram. Well, yeah, so one question is, will there ever be a problem where you have two slow steps? Not, there's always you'll always have one step that's the absolute slowest. In this class, it'll always be clear cut. There's always one step that's slow, and you know the other steps are really fast. The answer is no. I mean, do you end up in situations where the kinetics get complicated and then two steps kind of happen at the same rate? Yeah, I'm sure there are, but for us, no. And generally speaking, it's not. Yeah, you're told which ones are fast and slow. You're either told which ones are fast or slow, or you're given a, or we can kind of deduce it from this. You could be given a reaction coordinate diagram, for example, and that would tell you what the fast and slow steps are. Let's see, how do I want to get this all on here? So, yeah, I'll just call it to this. So this part of this curve here, so this is energy. And this is the reaction coordinate down here. This first part, let me actually, before I describe what each part is, each of these steps here, the fundamental steps inside of the reaction mechanism, corresponds to, in some sense, one of these hills. So the initial step, like in step one, I'm here, and I have to go over this barrier to get to here. So this is step one in the reaction mechanism. In step two, I'm going over the second barrier. And then in step three, I'm going over the third barrier. So that's the way to draw or tie together reaction mechanisms with reaction coordinate diagrams. It's that each step in this reaction mechanism corresponds to sort of a step or a movement over one of these transition states or barriers or whatever on the reaction coordinate diagram. So step 1, I get over this one. Step 2, I get over this one. And step 3, I get over this one. If we had a fourth, I wrote step 1 twice. If we had a fourth step, you would see it on the reaction coordinate diagram as another lump. And they don't have to, even though in this case they do kind of go like a waterfall, they don't have to be that way. And we can look at an example where that's true. But let's take a look at this. So this first part here is talking about this is the energy of this. And what I'm forming here in this trough that's not our product. This is an intermediate. So yeah, this is an intermediate. Ugh. I guess since we've kind of talked about intermediates already, so I don't have to necessarily define that. But so the intermediates in your reaction mechanism, I guess I should say, show up in these local minima on these graphs. So whenever you hit a trough where it's not the product or the reactant, you have an intermediate there. So this is an intermediate and this is an intermediate. Let's see. So then, yeah, what's our other intermediate? We can look at it right here. That's our other intermediate. I guess we have bromide pops up again. It doesn't really matter that much. And then finally we get to our products. So the chemical species that are described by the mechanism, these things all appear in the minima along this graph. So wherever you have these troughs in the reaction diagram, the reaction coordinate diagram, that's describing the different things that we can actually see in the reaction mechanism. These real, bonds have really been formed or broken along the way. And so we see the reactants here, and then we see that they get converted to the intermediates, and that's the first trough here. Those intermediates become this next intermediate, this purple intermediate that I've drawn here, and that's the next trough. And then that intermediate reacts with bromide or whatever, and then ultimately we get to our products. So intermediates are just these these are the local minima, right? And then this is the global minimum or whatever. The lowest trough down here ends up being the product. And so along the way, we have these 3 different transition states. So, we have a transition state here, a transition state here, and a transition state here. What would a step in equilibrium look like on a graph? What would that look like? Let me come back to that. An equilibrium step wouldn't necessarily look that different from this. Let's see. So yeah, so we have these different transition states along here. The relationship to the kinetics, though, is if we come up here and we look at this is slow, this is fast, this is fast. So we have step 1, we have step 2, and then we have step 3 down here. This is our slow step, and these are my 2 fast steps. And what we see is that the barrier here, the kinetic barrier that's the highest, like, visually that we can just see that, corresponds to the slow step. So this is our slowest step here. And so that's the relationship between slow and fast on this diagram, is just that the higher the little mountain is that you have to get over, so the higher in energy the transition state is, or the higher the activation energy is, or whatever, the slower the step is. So if you're looking at a reaction coordinate diagram like this, and you're trying to figure out, you're saying like, oh, which one, you're not given this, for example, you're not told which is slow and fast, to get back to somebody else's question earlier, and you're saying, okay, well, which one of these steps is going to be the fastest or the slowest? It's the one that's got the highest activation energy that's going to be the slowest. So typically that's whatever one just is like highest on the graph. So I guess technically you would be comparing the energy of the intermediate. You'd be looking at the distance between here and here, but usually it's just whatever one is literally like the actual highest. You don't have to do a whole lot of comparison there. So this is an actual chemical reaction that we're looking at here. This is, you can go ahead and do this in a lab or something. I just wanted to choose one that was real. But yeah, the rate determining step is this first step. So I'm here, it takes me a long time to get over this. But then this last part happens extremely fast. And so that more or less just describes, the whole reaction. So this, I guess, is, for me, this looks pretty familiar because I've been working with this stuff for a long time. The nice thing about these graphs is they describe a whole lot of things. Like if you look at the Arrhenius equation, where you're trying to calculate E sub A and all this stuff, the math can get pretty nasty. And here, even though this diagram is not super simple, it does simplify things down. I don't have any numbers on here. I don't have to worry about that. I have a nice, clean visual representation of what's kind of happening during the reaction. So I go through these three different transition states. So the transition states, the peaks here, those are not things that we can actually see here. They're sort of these weird chimeric intermediates, or I shouldn't use the word intermediate. They're these weird chimeric things that kind of form. So for example, in going from here to here, it's the place where bromide, you see how the chemical reaction that's happening here is you have a bromide bond to a carbon, and then that breaks to form this intermediate here. And so the transition state would be something like the bromide is kind of not quite broken off, like it is over here, but it's still not an actual solid bond. And so I just have this weird super high energy species in between. That's what the transition states are along here. They're sort of just these weird things that sort of fleetingly exist. So the way I have it drawn right now, is just one way that these things can appear. It doesn't, if we're just looking at, like, let's say, hypothetical reaction, I could have a reaction coordinate diagram. Let's look at this through like a problem. Let me think for a second. What do we want this to look like? Let's put it in terms of the types of problems we can ask about it. So let's say we have a reaction coordinate diagram that looks like this. It's just describing some reaction. We're not super worried about what the reaction is. What can we say? What kind of questions can we ask about it? So it's the same kind of analysis, right? We could say, like, how many steps are in the reaction mechanisms? How many steps in the reaction mechanism? In order to figure that out, all we have to do is count up the number of peaks that we have to go over to get to what is the, the final product. So this is going to be the product down here, and these are going to be the reactants. It's always that way. And so the answer to that is just 3. We could ask, what is the rate determining step. So if we just follow, let's just call this step 1, step 2, and step 3. Which one is going to be the rate determining step? It's going to be step 2, because it's the highest one. I'm trying to think if there's any other questions we can really ask about this. Where's my... Yeah, I think that's pretty much it. So you can kind of see how this could get drawn into a different problem though. If we give you a reaction mechanism, but we don't tell you, and we give you the reaction coordinate diagram, then we could not tell you what the rate determining step is, for example, and you would have to figure it out intuitively from this. I guess the only other thing I would say about reaction coordinate diagrams is that the height of these barriers is related to the rate constant. You know, if you were asked like which, is that 100% true? I guess I don't want to make that blanket statement. I'm going to say that you could say like which rate constant is the highest relatively speaking between these. It might get a little bit more complicated than that, but you can kind of think about it qualitatively at least, that the distance between here and here is kind of dependent on the rate constant, at least partially. So large values of K for rate constants are very fast. That means that you have small barriers to get across. So the larger K is, the faster the reaction is. So you expect the barrier to be small. If K is very small, that means that the rate is going to be very small. And so generally you're going to expect very large activation energies or very large barriers there. Yeah, the EA, I'd have to think about like the exact quantitative tie between the activation energy and the rate constant. But they're related for sure. You know, the higher the activation energy, you expect the rate constant to be smaller because you expect the rate of the reaction to be smaller. But since the rate depends on the concentrations and these kind of other things, I'm trying to think through that. Yeah, it probably is like directly tied. But for us, I think I'm gonna not put my foot completely into that and just say that, yeah, the rate constant, I would say generally speaking, the rate constant is smaller for larger barriers. So this one you would expect to have the smallest rate constant, and maybe this one would have the fastest rate constant. That's sort of the way that those things are tied together. So the last thing we'll talk about besides reaction coordinate diagrams, or sort of related to reaction coordinate diagrams, is just catalysts. So catalysts, if you look on the GChem website, there's like a lot of stuff on there. We're not going to get deep into them, but catalysts are super important for, we're not going to go into as much detail, I guess I'd say, as the GChem website. It's not that much. Well, some of this stuff's pretty detailed. Catalysts are super important. The reason they're important is because is because they're used all over the place. So we've been talking a lot about kinetics. The kinetics for reaction determine how fast a reaction is going to go, or in some sense, whether a reaction is going to go at a rate that's like reasonable at all. You know, like just because something can happen thermodynamically doesn't mean it happens on a time scale that is reasonable. So if you have a reaction, so for example, if we think about like graphite, like pencil, you know, what you use in a pencil, that's a form of carbon, like a carbon allotrope. Thermodynamically speaking, though, carbon as diamond is much more stable. And you know this even from just your interactions with, or I don't know, like interactions with pencil graphite versus a diamond. Diamond is very hard, and it's a very stable thing. I mean, they use them. I mean, in addition to using them in jewelry, they use them on the tips of saws and stuff like that because they're so strong and can get them really sharp. Whereas carbon that's in graphite form, you know, it's not. I mean, we use it to write on paper. It's not nearly as stable. The bonds are not as strong. And so energetically speaking, this is a much lower state. But on the surface of the planet, right, like under normal pressures and stuff, carbon graphite doesn't just spontaneously convert itself into carbon diamond just because it's lower in energy. So this is our reactant in a sense, and this is our product. So like, you can ask yourself, like, why doesn't that happen? And this starts to get into like what the real differences are like sort of tie together why thermodynamics and kinetics are both really important for chemical reaction. Thermodynamics tells us that graphite can be converted into diamond. And we know that's true because we see diamonds. And it even tells us that it's favorable, that this will happen spontaneously. But we don't see graphite if you just leave your pencil at home, and then come back and check on it after a month. It doesn't magically turn into diamond. And the reason is because the barrier, the kinetic barrier to getting there is extremely high. So you could say E sub A. Actually, let's just talk in terms of rate. The activation energy is very high, but I think it makes more, we've been talking about rates the whole damn chapter. The rate of reaction for this at atmospheric pressure, at least, and room temperature is very, very, very slow. So even though this reaction wants to happen in a sense, I'm anthropomorphizing it, carbon graphite wants to become carbon diamond, it just takes way too long. So, it'll just never happen because it happens on such a long time scale that, like the universe is over by the time you actually start to have any appreciable amount of diamond. So this reaction barrier here is important for that. So you can imagine that if you wanted to convert graphite to diamond, one way that you could try and do it is to lower this reaction barrier here. And so that's what catalysts do. So catalysts, they don't just work on converting graphite into diamond, and I'm not actually sure what kind of catalysts are available to do that. But one way you could do this, right? So you could put them under super high pressure and temperature. I think that's how they make synthetic diamonds. But another way you could imagine doing it is you could say, well, like, since that's our problem, since this thing is thermodynamically wants to happen, maybe there's a way to lower this barrier. And that's what catalysts allow us to do. So a catalyst for example, could be used so like with catalyst. A catalyst could be used to lower the energy of the transition state. So if we've got so this is without the catalyst, and this is with a catalyst. So what is a catalyst? A catalyst is something that lowers the energy of the transition state, at least in this case. There's like a very technical definition of a catalyst, which is that it speeds up the reaction without being consumed. And that's defined on the GChem website. But for us, what we can look at, and so there's a more general way to look at this than exactly what I'm telling you. But generally, or at least one way that they work, is they lower the energy of the transition state. But they're not products, or like, I guess you could say they're not consumed. I feel like that's always emphasized with catalysts, but they're not consumed during the reaction. So a very good example of catalysts that are not as wonky as this. This is an interesting application of it because it is a nice way to produce diamond, which is a very expensive, valuable thing. So, you know, if you're doing research on these types of, on how to make catalysts, it's like, well, it'd be great if I had a catalyst to do this, right? But a very good application of this, I know we're almost out of time here, is that in a car, you have a catalytic converter. It works under the same principle. So when you burn gas, one of the things that you'll get from incomplete combustion is carbon monoxide. You get a bunch of things actually that are nasty. Carbon monoxide, you also get nitrous oxide and all this kind of other stuff that's nasty. Let's look at carbon monoxide. The carbon monoxide gas is produced from incomplete combustion. So when I'm burning my, you know, like let's say I'm driving an old car and it's shitty, the engine's busted. I'm getting a lot of carbon monoxide that's coming off. We don't want that carbon monoxide going into the environment because, you know, it's poisonous. And so what you want to happen is to have it go to carbon dioxide. The problem is that that doesn't happen easily. So we end up in sort of a similar situation. I'm simplifying the energy diagram there. That doesn't happen easily without a catalyst. And so cars have catalytic converters on them, and the catalytic converter works to lower that barrier. And so catalytic converters have these precious metals in them like platinum and stuff. And the reason I bring this up is because it sort of emphasizes this last part, that they're not consumed during the reaction. And so you can imagine that if they were consumed in the reaction, it would be a pain in the ass because your catalytic converter would have to have enough whatever in it to react stoichiometrically. But since it's like you would have to continue like changing out a cartridge or something, kind of like you do with like a filter for a refrigerator for water, you'd have to change it out. But since it doesn't react, it's not consumed during the reaction, all you have to do is have your catalytic converter, you put platinum into the catalytic converter, and it works over and over and over and over and over again. And so that's why, you know, you don't have to change your catalytic converter out. You do, they eventually go bad, but generally speaking, they don't, generally speaking, they're not really reacting, right? So our catalytic converter might be something like platinum metal. And as the carbon monoxide runs over the catalytic converter, it has some interaction with the platinum that lowers the activation energy and allows it to become oxidized to carbon dioxide. So that's sort of like an everyday example of where you kind of see catalysts in action. All right, I have office hours in like 4 or 5 minutes. I will take a break. But this more or less caps the type of material that we'll see. I doubt we'll talk any more about. There's other stuff we could talk about with catalysts, but I think that's fine. So yeah, I think this is an okay definition for us. There are other ways that catalysts can work. It doesn't have to be lowering the activation energy, but that's a good way to think about it. So yeah, so that caps the material that'll be on the exam, and Ryan will post. Yeah, so no Arrhenius equation. I wouldn't worry about that. It'll just be quantitatively. It'll just be all the rate law and kinetic stuff that we went over. But no, I'm not going to ask you to calculate the activation energy. I guess I wouldn't have minded talking about. Nah, it's fine. I was going to say I could talk about temperature dependence of Arrhenius, but it doesn't really matter. All right. So yeah, so let's cap it here, and I will see whoever comes to office hours in a few minutes. Okay, let's take a look here. You guys already have some questions posted.
Can
Was
you
that you
hear?
asking about what the equilibrium steps would look like on a reaction diagram? I think so. It looks the same. I didn't want to get too deep into that. It looks the same. It'd just be that the whatever the intermediate is and the reactant is. Oh, I can't. Hold on. Maybe my speakers are off. Oh, I can hear you now. I heard somebody at least. Taylor, briefly.
I have a question about number 4 on LE 3.07.
Yeah, I can do that. This is the radioactivity one. So we're looking at number 4.
I understand how they solved it, except so they use it in counts per minute, but they calculated the K using years. Why don't you have to convert the years to minute and then calculate K?
All right, let me look at the question for a second. Let's see.
I think you get the same outcome even if you convert. I got the same outcome.
Let's see. Okay. Disintegration rate of 15.3 counts per minute. Carbon 14, 57. Test the map of the pocket Geiger counter and get 15.1 CPM. Let's see. So, yeah, let me go through really quick. So we've got the half-life. Are you asking about the years thing? Let's see. So yeah, so you've got 5,730 years. So we're trying to pull K out, I guess, here. 5,730 years. 0.693. Years. And then, yeah, you just plug in 15.1. Yeah, then you just plug in values. Okay, so what's your question, Taylor? Now, I'm sorry, I'm just getting familiar with the...
You use counts per minute for the other values, but I just wanted to know why you can use years for K. But
yeah, I'm sorry. Yeah, okay, I see your question. Like, why can you use years even though it's in counts per minute? So, yeah, it's confusing. So we didn't really talk about this in class that much, but like I think so in the Geiger, so the counts per minute thing like makes it feel like it's talking about a rate because it is literally a rate. You know, it's saying counts per minute, but it's not being used in that sense in the equation. So the counts per minute it's sort of measuring the concentration. I think that's what's really confusing about it. So if you forget about the counts per minute part, it's saying that you're starting out with a concentration of 15.3 units and you're ending up with a concentration of 15.1 units. So if you look at how that's, if you look at how you plug it into the equation, we're going to plug that into the normal first order rate law equation. where does the 15 point, even though it's in counts per minute, it's like this becomes 15.1 counts per minute over here. All right, we're treating it as a concentration. So really I should get rid of this because we can't take the natural log of those units. So the counts per minute on the Geiger counter, you can just think of it as telling you it's not a measure. It's not related to the, God, I don't want to say this in the wrong way because I know it's already confusing, but it's not related to the rate, or at least it doesn't come into our calculation here for the rate. So it's like, I'm trying to think of a good analogy. I mean, I think you can just think of it like if you're, the counts per minute is a measure of like the radioactive decay process, you know, like how much energy is coming off. So I forget what they measure. I think it's like beta particles or something like that. Yeah, light years is what came to mind as well. But if you think about it in terms of like, let's just think about radioactive. Let's put it off to the side, the counts per minute thing. Things that are radioactive, that are really radioactive, are hot. And so heat isn't a measure of concentration, of course. But if you were to go out and like use your hand, which I wouldn't suggest, but if you were to go out and use your hand and like put it near two different objects, and one is much hotter than the other, what would you infer about the one that's much hotter? It has more radioactive material in it than the one that's cooler. So that's sort of the thinking here as well, is like, since you're measuring the radioactivity of the material, like you're not measuring heat, you're measuring some other particle or whatever, the more counts per minute that you get, the greater the concentration of the material inside of the whatever you're looking at, like whatever the paper is. And so we're using CPM as a proxy for concentration, I guess is what I'm trying to say. And so even though it's in minutes, it doesn't really matter because the minutes don't actually enter into the equation. And if you look at the rate law equation, these units here for A and A sub O, like they don't have to even have dimensions on them. You know, we can look at problems where these are dimensionless. It's more the relative quantity between these two. So that's why it doesn't matter. And yeah, it's confusing. Does that make some sense, Taylor?
Yes.
Yeah.
Thank you.
Yeah. No, I found that confusing as well when I first read it. I was like, I don't know. But yeah, that's all it is. Yeah, so I guess the another way to one thing to say is just like, in terms of what the units are in the rate law, I'm sorry, in the rate constant, it, regardless of what these things are, as long as these it doesn't matter at all. But in terms of what this needs to be, it needs to be in agreement with T. So if T was in, let's say, well, yeah, so here, because you're using concentrations and calculating T, it doesn't matter. But like, let's say you're in a situation where, you know, where you're given the rate constant and you're given time, those two things have to be in agreement with one another. Otherwise, it doesn't matter. So like, if you were given, instead of being given like a concentration here, let's say you were given like, you were told that like K is 1.2 times 10 to the minus 4 years, and then but the initial concentration is 15.3. When it said like how much is left over after like 20 seconds, then you have a problem because your rate constant doesn't agree with your time units. So you can't use seconds for time and years for rate constant. Otherwise, you're fine. So it's just looking at these two things. I guess that's another way to kind of think about it. All right, so we've got number 4 on 3.10. Yeah, I wish we had more time to talk about catalysts. Those are probably the most interesting part of this chapter. Let's see. Oh yeah, so question 4 is one where, I mean, we can work through it if you want to. You would just use the Arrhenius equation for this, but I'm not going to test you on this. I think it's just, I haven't worked through this problem, but I think it's just a plug in some numbers type thing. But yeah, number 4 on 3.10, we're not going to do that on the exam. So we can kind of, no, yeah, I won't make you use those equations. I don't care about them. So you just don't worry about that. All you have to know about the activation energy is just like some qualitative stuff and how to analyze the reaction coordinate diagrams. I'm trying to think if there are other equations involving activation energy, but I don't think there are, right? It's all, the main thing to worry about, I don't know why they lump that, why the material is organized such that it lumps the activation energy on. I guess it makes sense conceptually, but mathematically it becomes sort of this weird sidebar type thing. But yeah, we're worried about method of initial rates and the integrated rate law. Those are our two sort of quantitative things you want to master. Calculating the activation energy at different temperatures. Yeah, you know, it's not like it's a hard thing. It's just like another thing to worry about that we don't need to. Number 2 on the homework. If you go on to take thermo, like if you take a real thermodynamics course, you'll get into all that stuff in a lot more detail. Okay, so yeah, so this one, so this problem says we've got A plus 2B goes to C. And a key thing about this is it says A and B react to form C according to the single step reaction below. So it's a single step reaction. So this is an example where the overall reaction is also the reaction mechanism, even though it's abstract. So like, you know, things that happen in a single step, it's not, you know, the overall reaction necessarily is the reaction mechanism. And that's kind of what's going on here. And then it asks you, what is the correct rate equation for B and the correct units for the rate constant? So rate equation. Yeah, so it's asking for the rate law, presumably, and the units for K. So because they're telling us explicitly that it's a single step reaction, we know that this is this overall reaction here describes, we can use that to write the rate law out. And so they're asking you to write it in terms of B. So let me look at where they're, okay, yeah, that's how they're writing it. So yeah, so we've got dB dt or d delta B over delta T or whatever. And then we want to write out the rate law for it. So usually if they're asking for the integrated rate law, they'll say integrated rate law. Otherwise, they're typically talking about the differential rate law, which is this where we started when we did the method of initial rates. So let's see. So we want to write this in terms of B. Yeah, let's see. So like. Yeah, we didn't touch. I'm assuming your confusion's coming in on where this 2 is coming from. So the coefficient that's out front here will come and be included on the side of. It depends. I guess it depends on how you define it, but I think generally speaking, sorry, let me think about how to explain this really fast. So if we were to if the question was write out the rate law, let's say, for the reaction, like I would write it out as rate is equal to K times, let's just start there, that makes sense. I would write it out as this. And so this describes the rate of the reaction. But in doing this, we have to, what is this really describing the rate? So when we think about the rate of the reaction, we have to think about it in terms of like the change in one of these concentrations with respect to time. And so this rate, the way it's written, let me use delta. Describes the change in A with respect to time. That's usually how we write it. So whatever has like the stoichiometry of 1 over here, we kind of set that for the rate. If we're talking about B though, the change in concentration of B with respect to time is not going to be equal. These things are not perfectly equal. And the reason for that is because we have twice as much B. I'm sorry, the stoichiometry on B is 2. So B disappears, let's see, twice as fast as A. So for every mole of A that reacts, 2 moles of B react. That means that if 1 mole of this disappears, 2 moles of this disappears. So what's the relationship between delta B, between these two things? Let's see, this, I guess the right way to probably write it is like this. You would say that delta B, or no, sorry, on the other side. Delta B, delta T disappears at a rate that is half of
the previous version. On the question, the half is in front of the B over T.
on the question on the previous version.
For number 2, they give you this delta B over T. It has a negative half in front of it.
Delta B, delta T is negative 1/2 in front of it. Give me 1 second. Why do I not see that on mine? Oh, and I see in the correct answer choice or whatever. Yeah. Let me think for 1 second. Does that make sense? So the change in A versus the change of B. The rate. I'm trying to think if I agree with that or not. Oh, come on, brain. let's think about it. Let's just take our time here. So if we start out with A at some particular time, let's say we start out with 1 of A and 1 of B. So at some particular time, let's say we start out with 100 of this and 100 of that. And then like whatever, enough time passes to where we have 50 of A. How much B will we have left? We'll have 25 B. Yeah, okay. What does that tell us about the rate though? So this is with respect to the same time increments. Okay, yeah, all right, yeah, no, that's right. Yeah, I'm sorry. So my thought experiment around that, I didn't mean to make that, put that, like all I said to try and figure out what the coefficient should be in front of that is if I'm starting with the same amount of B's, and I know that B disappears twice as fast as A because that's what the reaction tells me. That part makes sense to me intuitively. That if I start with like 100 of A and 100 of B, so I have equal amounts, and I wait some time t, whatever t is any time, we'll call it t1 or something. And let's just say I arbitrarily choose now that A is going to be 50. So that's how much of A is reacted, 50% of it. How much B will I have left over? Well, I can see that B is reacting twice as fast. So that means that, shoot, now I've confused myself. B is reacting twice as fast.
Someone put it takes twice the time for B to lose the same amount as A.
Oh, give me 1 second here.
That would be half the time, right?
Yeah, I think it would be half.
B should be all right. I know. So I'm sorry. Like my brain needs to reset. B disappears faster than A. Right. We all agree on that. Like
You think of it as 2 times delta t?
Yeah.
Because we're dividing by 10, right?
Yeah, twice as fast. Okay. That's a good way to think about it. Jesus. I need to get more sleep at night. All right. So we've got delta A, delta T. I'm sorry, who asked this question? I'll make sure I'm not getting stuck on like, yeah, it's okay, sorry. It takes twice the time for B to lose the same amount as A. Twice the time for B. Yeah, that's a good way to look at it. It takes twice, okay, that makes sense. Thank you, Joshua, Jesus. Yeah, all right, cool. So we just multiply delta T times 2. That's a great explanation. That's way simpler than the way I'm trying to think about it in terms of concentration and just getting really confused. All right, so as Joshua said, and I think Ian came over the intercom and said, because you have twice as much B, yeah, it takes twice as much time for B to lose the same amount as A. Twice as much time. Well, is that true though?
Well, I think it's half the time, but you say 2 times delta t, right?
Half the time. Yeah, it takes.
We could say like 2 times concentration of A instead over delta t.
No, I think you had it right there. That's it. It takes half the time for B to lose the same amount as A. That's the right way to say it. Half the time for B. I don't know if that's exactly like a super clear technical way to write it, but half the time for B to lose the same amount as A. So if we start out, let's say with let's go back to, let me try this again. Hopefully this doesn't turn into a nightmare again. But if I have like concentration of B and I have concentration of A. And let's say that the initial concentration for both of those is 100, just because it's an easy number to work with. We're saying half the time for B. So at T equals, like, let's say 1 second and versus T equals 2 seconds, you could end up in a situation where, like, let's say that I guess we don't know exactly what, let's say, so B would be at 50. What does that imply about A then?
And A, would it be like at 75?
Yeah, 75. Yeah, because you're losing 25. That's right. Okay, perfect. Yeah, all right. Yeah.
So then you would say that in order for B to get to 75, it would take half of 1 second, basically.
That's right. That's right. Yeah.
Okay.
That's really the whole thing. I just, like, my brain is just like, but yeah, it doesn't, it, like, I guess, or maybe it is just a kind of confusing concept and I don't really think about rates that much. But yeah, that's, I guess that explains why it's fractional like this.
Yeah, it's just like B of T or delta B over delta T is faster. We could set, we could have the coefficient from delta B and delta T to be 1 and just put like 2, like that is 2 times faster than the rate of A of over
Right.
A of T.
So, like, this would be an also alternative way we could write it.
Yeah.
And then
so like we were thinking of it that way, but we weren't writing it out that way.
Yeah, right. This, I guess, yeah, for me, this makes more sense. And you can see that these two things are equivalent, like even algebraically. Like if you solve for the, you can move the 2 down here and have the same expression. You just get this right back out. Yeah, okay. I don't know. All right, Taylor, was it that you that asked that?
No.
That Josh that asked that? Joshua?
Yeah, it was me.
Okay. I don't know that I was actually helpful there. I think you guys probably helped me more than I helped you, but is it? Yeah,
Yeah, I guess so. I guess what I had a question with, so I understood like the rate equals negative change of A over change of T, and then that equals change of B over 2T. But then I guess I was confused as how you got the negative 2K AB squared, like, because that's the final rate or whatever for B.
Oh, why is the 2 come out front?
So you just, yeah, I guess do you have to like multiply it to the other side or something?
Yeah, so I think I'm trying to, I guess it feels a little bit arbitrary to me, but like if you wanted to write out, I get bogged down in my own, like, something that's unrelated to your questions. So I have a tendency to do that sometimes. All right, so anyway. So yeah, so the rate is whatever, like delta A. I'm just not even going to try and think about it too hard because I'm just too tired to make sense of life right now. But so this is the relationship between the rates for the reasons that we talked about. But this is actually related to the stoichiometry. And we don't really care about this. Rarely do we talk. We could talk about it in that. But so since we're saying if we define the rate, I guess it, like, what I'm thinking is arbitrary is like if you define the rate like we're defining the rate here, we're using, it seems like the convention is you take the rate and you define it in terms of like whatever has a coefficient of 1 for the reactants. So, we say the rate is equal to negative delta A, delta T, and that is equal to negative 1/2 of delta B over delta T. I guess regardless, yeah, I guess it's not really a convention. I guess regardless, this is going to be equal to the rate law. So if you want to, it's to whatever, this rate expression is over here. So if we want to say, if we want to write, I guess, the rate.
Is it easy? Is it kind of because A is our our rate limiting factor, or?
No, it has more just to do with just some simple, like, so if you're defining the rate as some number, like let's say the rate, let's say the rate is equal to this over here, right? So this describes, if we're talking about it in terms of A, whatever number over here is going to describe the rate of change that we're going to see for the concentration of A.
Like if I could try to like explain it just to like help myself, I guess.
Go ahead.
Like
Yeah.
if you have the rate, so you say it's KAB squared for change of A or change over T.
Mm-hmm.
So all you're doing is if you have -1/2 change of B over change of T, like if you're trying to isolate the change of B over change of T, you just multiply times 2, right? That's pretty much how you get the same.
Yeah, sure. I think that's a fine way to think about it. Like,
Because yeah, I guess I was trying to like figure out like what I'm trying to like isolate to get the rate, if that means. And then also like I was confused as to why C didn't come into the equation, but I guess since it doesn't really count for the rate law, right? The product.
I mean, you can talk. So yeah, it doesn't matter. So C is fine. I was just saying, like, we're not worried about that because we're not talking about it. C is what you choose to monitor the reaction of the rate. I guess the thing that's making this confusing, aside from me getting confused, is just that how you choose to monitor the rate of the reaction is dependent on like what you're looking at. So you can look at the appearance of C. When we look at this chemical reaction up here, we can look at the appearance of C and determine the rate of the reaction that way. So we can say, well, like, how fast is C appearing? We could also say how fast is A disappearing, or we can say how fast is B disappearing. And so, it's sort of up to us in terms of like what we want to look at in terms of experimentally, in terms of how to like measure the rate. And so with the question, I think all the question is really asking is saying, well, if we choose B, like we say we want to look at the rate of the reaction. Let me go check the question again. Following is the correct rate equation for B. They're asking for the correct rate equation for B. So they're saying we want it specifically for B. Tell us what the rate looks like, the change in B with respect to time. And that is, if we want to know what that is, like if we're defining the rate, we're saying, okay, we want to know, we're saying like, we want to understand it this way. So the way we're choosing to monitor our reaction is we're going to look at how B changes with respect to time, instead of looking at like, let's say A with respect to time. So this is how you would kind of look at that, right? You would go in and you would say, okay, well, I'm going to take a plot, I'm going to measure B, and I'm going to measure T, and I'm going to get some points along that plot, and I'm going to see, how B changes with respect to T. That's what I'm trying to measure experimentally. So what am I expecting the rate to look like for that? Like, how would I express that in terms of the differential rate law? And so that's what we're trying to figure out on the other side here. And so that's why the 2 and everything comes out on the other side.
Yeah, and that makes sense. So like if KAB squared is like the rate of A disappearing, and if we're looking for the rate of B disappearing, since it disappears twice as fast, makes sense to have like a negative or like a 2K AB squared, if that makes sense.
Good.
Since it's disappearing twice as fast as A.
Yeah.
Okay.
And like that's what yeah, exactly. Like if you know the rate law, like if you knew this rate law and you wanted to make predictions about the rate at a particular point in time, this is how you would do it. Right. So if I'm like, what's the rate? Like if I was to say like, what's the rate, at a particular concentration of B, you would use this to figure it out. What you said is good. If you're asked, like from a problem solving perspective, because I'm doing a shitty job of kind of explaining this conceptually, from a problem solving perspective, if they ask you for the rate equation for something in particular, like A or B, then you start by writing out like the relationship between the rates. So like delta A to, like what we did here, we said, okay, delta A over delta T is going to be equal to half of delta B over delta T. And then the second part of that is you just set it equal to the integrated rate law and isolate out, whatever you're looking at. So you isolate out delta B, delta T here, so you have to use the negative 2K. The same thing is true if you're asked in terms of A, it would still be equal to, whatever this is, but you would want to bring this negative over to the opposite side. That's all that's going on there.
All right, thank you.
Yeah, thank you. I think you did most of the teaching there. So let's see.
Did you ever talk about number 4 on the LE 3.10?
Yeah, we talked about it. Well, only so much in that I said you don't have to worry about that for the exam.
Okay.
Was there a particular part of it that was confusing, or?
I was just unable to do it. The explanation is, I'll try to look at it, but
Yeah, I mean, if you're interested in knowing, just for like the sake of knowing, we could talk about it. Like maybe ask next office hour or something. But since we have an exam coming up, let's just stick to the other stuff. It should be, those problems should be just like you're plugging in numbers, but maybe there's some like tricky crap in the problem or something.
Yeah. And for number 6, it looks like I kept getting like 16.6 kilojoules, and it seems like I'm calculating like the change in E of A, but I don't know how they got 89.3.
Oh yeah, just skip this one. Anything to do with, I should make an announcement about that.
Okay.
Let me actually make a note real quick. Anything to do with calculations around oxidation energy, just skip it. So we're just not going to do that. I don't think it adds a whole lot.
And I know like on the GChem for exam 3 talks about a little bit about nuclear chemistry and like fission and all that stuff and all the different terms.
Oh yeah, no, we're not messing with that. Like all you have to know about nuclear chemistry is that it's the, what we talked about with half-lives. The question Taylor will talk about, or like, the things that are in the modules related to nuclear chemistry.
Okay.
But yeah, we're not like fission, fusion. No, we're not messing with that. Some instructors get deeper into that if they're like interested in it or know a lot about it. But I know a decent amount about it, but I'm just not. I don't really care about it. Yeah, I'm looking at this Arrhenius thing right here. I'm not sure, just looking at it, where things are going awry, but it should be just plugging some numbers in. Yeah, I don't know. I'm not going to get bogged down in it just because we're not going to deal with it. Those equations, the problem, one of the reasons I don't mess around with them, I don't know, I'd have to talk to one of the physical guys of whether or not this is a good rationale, is because like, they're not like the Arrhenius equation and all those equations. I think they're not, well, one, we just don't have enough time, but also I think a lot of times like you end up needing calculus to do anything interesting with them. And like, obviously we're not going to mess around with that. So, but yeah, so if you've done the integrated rate law and all the other kind of crap that we've worked on and you get the reaction mechanism stuff, you should be good. The Arrhenius stuff, just don't even worry about that. Yeah, so like question 9 would be another one that you would skip on this homework.
So their review that they're having like includes like Arrhenius law and stuff like that. So would it not be a good idea to like attend like their TA's review and stuff? Because I'm assuming that their test is going to be a little bit different from ours.
There might be miscommunication from, you can attend their, well, I don't know exactly what Samoilenko has gone over, but I'd get our TA to coordinate with their TA. So that things are kind of the same. There might have just been some confusion around the Arrhenius equation. I can assure you that we won't see it on our exam. If the TAs in that class go over it, I just wouldn't worry about it. But most everything else probably should be aligned with what we're doing. So I would say it's worth it going to their review.
Okay. And as far as like solubility goes, do we like need to review that before the test or?
Yeah, just in terms of like kind of what we went over. Yeah, you should know solubility. I forgot about that as being part because it's kind of left over from last exam. There'll be some solubility questions on the test. Yeah,
How did you find out about the other classes review?
that I don't know.
I was talking to like whoever was
Yeah,
saying.
Last time it was like posted in Piazza or something. I think they shared it through there or something.
I can look up where the review is.
Ryan might link it, or we can ask him, because that's what he did last time.
Yeah, I can get it. Yeah, I assume Ryan will just post it. Let's see. I'll just make a note so I can do it later. So post links to other sections review. I'll remind everybody that solubility is on the exam. Okay. Yeah, okay. Anything else?
What's if we're ever told like something's at room temperature, what do we assume that to be, like at like 200, 300
Yeah.
Kelvin or?
We should. I hate when they do that. But yeah, I think it's what 298 Kelvin to 25 degrees Celsius is considered room temp. But usually, if we'll write out what it is if you actually need the number.
Okay.
But yeah, 25 degrees Celsius is used as standard room temp. That's not what it is. I keep it cooler than that at my place, and I don't know why that's. I don't know why. I don't know if that's like standardized by some standardizing body, but that's what people say. Other questions?
Will there be a? I really like the videos for the learning modules that we had for this unit. Are there going to be more of those in the future for the other modules?
The ones that Kate did.
Yeah.
Yeah, I think so. I think I'll have to go through and look at them. I don't know off the top of my head, but I know. I'm guessing, just looking at them, I'm guessing that Bieberdorf redid them like once the pandemic hit for the rest of this unit. So that's probably why they were updated for that. So hopefully.
Who else read that, John?
What's that? Oh, I'm sorry. So like let me make sure I understand what you're asking. So you're saying like you like the videos that are kind of embedded inside of the learning exercises for this unit?
Yeah.
Yeah. Let me look at the next one. I'll just tell you.
Did another professor do it?
Yeah. Dr. Bieberdorf, I think, makes those. Oh, this looks like, oh, wow, it looks like, I think that's Dr. McFord from a long time ago. Looks a lot younger. So it looks like there are videos embedded in Unit 4. I don't know how they compare to the ones embedded in Unit 3. It looked like some of the ones inside of Unit 3 were like recently reworked.
Mm-hmm. Okay.
But yeah, I think they're in there. I don't know. Those are more those are like a coordinated effort between the instructors that usually do that almost always teach general chemistry. And so they usually make those. I'm trying to look through them and see.
Also, is there like a poll or something we could do for like? Because I was fine with how things were when we had a flip class.
Oh, the other way around.
Yeah.
Yeah.
It feels like we're falling behind a little or something. I don't know.
Let's do it this way. I think this chapter, like these two chapters here, are they're just a little bit compressed because of Thanksgiving break. That's all. So we'll probably just keep doing it this way. I think we're fine on terms of time. So we're once we get through rates, that's like most of the material, and the next chapter is just electrochemistry, and
Okay.
And we should be good. So. But yeah,
Okay,
this whole thing was compressed. I realized that when I was making the like putting the learning exercises and stuff together, I was like, well, we've got 2 weeks as opposed to 3. So
How does this exam compare to the other midterms?
in terms of difficulty,
Or yeah, I guess like grading distributions, is it relatively the easier, like the best scored one?
usually it's usually like the first, third, and fourth exam. So units 1, 3, and 4. The grades are usually pretty good. Like I was looking up the historical data for the classes, depending on how you define pretty good. And then obviously unit 2 is really low. So if you, whatever, but for some reason this semester in our class, unit 1 was rough on people, and I think there's, obvious reasons why this is a different semester. But so I think that the exam grades are usually on par. So if you unit 1, whatever you did on that, assuming that the class behaves in this, this kind of way I'm thinking in terms of the median, that's what you should expect for unit 3 and unit 4. Unit 2 is just the oddball one, and that it's like a lot more challenging for students. So,
were there any points given back on the exam too?
Yeah, I remember your question. I don't think you're gonna get your points back.
Why? I did the question right.
Yours was about like significant digits, right? It was like It was a solid argument. But yeah, I think that one's. I understand your point, but I think it's like. Like technically it's correct, but it's like a rounding error on it. You're gonna be fine in the class. I'll make this deal with you, Ian, right?
Yeah.
Yeah, if at the end of the semester it matters for your grade, just let me know and I'll fix it.
Okay.
About that.
Okay, deal.
I don't think that was a general problem. But yeah, unit 3, unit 4, these should not be that bad, hopefully, and then we'll get through. It'll be the end of the semester, and then hopefully, I guess in the spring everything's going to be online. But then by next year, hopefully things will be back to normal.
And this is your first time like teaching 302 online, right? Because usually you had last year's first semester pretty smooth.
Yeah. Oh yeah, for sure. Yeah, but I don't usually teach online at all. Yeah, 302 online. This is the first for me for sure.
Yeah, because I'm taking your OChem class next year, and I was just wondering, like, I guess you probably have more experience teaching OChem online because you had like half your semester online.
Yeah, last semester we taught half of it online. So yeah, I had more experience with that, and I have more experience just teaching organic chemistry in general. So, general chemistry, I tend to like some of the topics I know extremely well, and then some of them I know less well because it just kind of depends on what you specialize in. So I just haven't taught the course as much in general. But yeah, OChem I taught online last semester. It's challenging to teach online. I think it's really challenging for the students. I'm still just trying to figure it out. But I think in general, we're all just trying to get through the damn thing.
What's the main challenge for students in that class?
In organic?
And like, what's the difference between that class and this class?
They feel radically different. So that class, so organic chemistry doesn't have a lot of math in it, really any math. So it just feels completely foreign in that way. But the main challenge I think for students is like, it's usually the first class where students you can't, it's extremely difficult to cram for. And I think a lot of students hear that a lot. Like, like I say that in this class, and it turns out to be true, at least for the acid-base chapter. But organic chemistry is like the first class where that's really not true. Like if you just try and wait and start falling behind, then you'll start drowning, and it's cumulative. Every single exam builds on the last exam. There's no like disparate things. And so there's just like once you start to fall behind, you just start getting crushed. So I think that's the biggest challenge for students, is just organizing their time. And then after that, it just comes down to sort of like, some people are better at getting it than others. Like some people just really struggle to kind of internalize the stuff. It's sort of a weird, I don't know how to describe what's challenging about it. It's very like pattern recognition oriented. And there are like a lot of exceptions and stuff. There's just you have to memorize a lot of stuff. That part sucks as well for students. And then on top of that, the problem solving is really hard. Like I guess that's really what it is. You have to, one, remember a ton of stuff, and then two, apply that stuff in like these fairly abstract problem solving things. So I don't, like if you were asked to memorize like 3,000 words or something, that would be a pain in the ass, but it would be hard. But all you'd have to do is regurgitate the words. In organic chemistry, it's kind of like you have to memorize 3,000 words, and then you have to like use those words to like solve, you have to use them in like a creative way. So you have to like really, really know them. So, but I think mostly it's just the speed of the course and the sheer amount of material that we go through is a lot in organic chemistry, and you could easily spend a semester on any one of the topics in there. So
Are there a lot of TAs in that class?
we have more TAs because the classes, well, online it won't be, but generally we have more TAs because we usually do, what do you call it? Free response for the questions. Like I don't do any multiple choice during the normal semester. I don't know. I guess for me, I found organic chemistry a little bit easier when I was in college because it's much more focused. Like after you get through the first half of the semester, you kind of know what to expect. Like it's not easy, but you at least know what's coming. I found general chemistry kind of confusing because it just jumps around so much,
Yeah, that makes sense.
So
And OChem deals more with like what exactly? Like I guess just like
it's reactions. Like you look at, so like all of general chemistry is like this kind of, I feel like it's really confusing. It doesn't give a good idea of like you don't learn any chemistry. You come out of the course and it's like you don't actually know any chemical reactions. But like that's what chemistry is. Organic chemistry is all about chemical reactions. So like for example, like how to make molecules, like if you want to start with some basic like oil, like you start with a molecule and you want to make it into a different molecule, like how do you do that? That's organic chemistry. So like let's say I start with I don't know, like if you're like clandestine drugs come to mind all the time just because they're easy examples. But if I want to know how to take like Sudafed and make it into methamphetamine, like organic chemistry sort of tells us how to do that. It also tells us non-illegal drug type things. Like if I want to take, if I want to make like Aleve or something or aspirin or something, I can make that as well. So it tells you how to do transformations on molecules that make them into other molecules. That's really what it comes down to. It's a lot of, so you have to remember a lot of reactions, and then you have to learn a lot of reaction mechanisms. You learn how to write reaction mechanisms really well. It's sort of its own contained world. It's not, I mean, I don't know, I have a PhD in it, so obviously I'm going to say it's not that bad. It's hard, but it's not as hard as people make it out to be. I think it just depends on the student too. So, and what classes you're taking. Some students will take OChem and genetics and like 3 or 4 other difficult classes. And I think that can start to be really problematic because it is, if you really want to actually understand it and do well at it, no matter how smart you are, it takes a lot of time. Like you should be looking at like 10 to 20 hours a week. Certainly by the second course, which is the really crushing one, you're starting to look at things where you're studying a lot every week, like hours and hours and hours. So just carve out time.
Should you take the OChem 1 and the OChem lab at the same time?
Do I recommend that, or is that the question?
Should you? Like, is that a good idea?
I mean, OChem lab is, I don't know. I wouldn't say this. I probably would. OChem lab, you just kind of want to get out of the way. It's whatever it fits into your schedule. I wouldn't worry too much about whether you take it concurrently or not with it. I wouldn't wait too long after OChem 2. I mean, some of the stuff you do in OChem 1, some of the stuff you do in OChem Lab, it doesn't follow synchronously with the lecture part of the course, so that can be a little bit annoying. But it's not like, it's just a very different thing. You're just like writing lab reports and stuff. You can definitely do it while you take Organic 1 if it works better for your schedule. But if you want to actually know the reactions and stuff, yeah, you maybe do a better job just taking it afterwards. But I don't think it really matters. I'm like kind of down on teaching labs in general. Like I don't think that students learn a whole lot in the instructional chemistry labs, and I wish that like higher education would come up with a better solution. So I'm not a great guy to ask about that. So that's why I'm like, just take it and get through it. But it's not like, my experience with that is not that the students don't, if you talk to other students who've taken organic chemistry lab, they can give you a feel for kind of what it's like, but it's not technically challenging. I don't think most students would say, oh, this is like a really technically difficult class, but it can be challenging sometimes to kind of figure out what the hell you're supposed to put in your lab reports. And it may have changed a lot. I haven't looked at the content in there in like 3 or 4 years. And I know Fetlin, the instructor for it, has changed a little bit over the years. So, but yeah, I don't think it matters that much. I wouldn't wring my hands over it. Just make sure you have time, because it's just, you know, you got to go in the lab and write out these lab reports and stuff.
None of those labs are administered online, are they?
No, they're not. People show up in person to take those labs. So if you're not in Austin or immunocompromised or something, that's something to take into consideration. I know they do, just from going to meetings and stuff, I know that they are pretty strict about kind of how they organize them. It's not just like, 50 kids packed into a place and they do temperature checks and stuff. So it's, it's safe. It's reasonably safe. But, you got to kind of consider your own risk profile. Yeah, so they're in person. They're probably, if I had to guess, they're probably like scaled down a little bit from what they usually are right now. Just because of limited resources, like limited number of TAs who want to come in, limited number of students who want to go in. If you could take it during the pandemic and you're not worried about your health, you're not if you feel comfortable kind of being in person, it might not be a bad idea. You probably have more, it'd probably be smaller class sizes. You probably get more personal attention, and they might be even doing like less labs and stuff. So it's not a bad idea to take it right now. But yeah.
And is OChem pretty much structured the same as this class?
In what sense?
Not just like, 6 LEs and then homework, and then like 5 LEs homework, and then.
I don't really mess. I don't have, at least for my course, I don't know. I'm trying to think of what Shabira does. Most of the organic chemistry profs don't use learning exercises at all. I usually, for organic chemistry, I try to follow the other Gen Chem instructors' leads on how they teach this course, just for consistency. But like in organic chemistry, it's just a matter of like, I just assign there's just a lot of homework. So, it's lecture, and then here's a ton of homework to practice it. My view on organic chemistry, I guess, is that like, there's no singular component of organic chemistry that's really difficult. Like if you just take one particular part of it, like at the class, like one part of the material and trying to understand it, most students can get it. It's sort of, there's so much of it to understand that that's what makes it kind of difficult. So it really comes down to, more than anything, just like working tons of homework problems. So like last semester before the pandemic started, I would hold weekend study hours in a big room, and we would just sit down for like 6 hours, and I would just sit with the students and like work problems with them. That's the ideal way to learn it, is to just sit with somebody who understands it well, like me, or like a tutor or something. But tutors are expensive. But you sit down and you just work problems for like 5-6 hours straight. So that's what it's geared towards. All the learning exercises and stuff, they're not, for organic chemistry, they're not super helpful. We're not trying to look at least in my opinion, you're not looking at like here in this class, it's like you look at kinetics and you're trying to talk about like how molecules collide and all these different types of things. And, that might require some sort of conceptual demonstration, but in organic chemistry, it's a little bit, the problem solving is a little bit more straightforward. it's just different. So, but yeah, I guess just the main thing is, regardless of whether you take it with me, I think I'm assuming Somolenko is teaching it next semester too, and he's a solid OChem guy for sure. The main thing is just make sure you have time carved out in your schedule. And I don't know. I think it just depends on the student. Some students don't. Some students get it easier than other students. Like it just gels with them better for some reason. But everybody has to spend a lot of time on it. Even people who like it or are good at it, you end up spending a crap ton of time on it. So.
All right, thank you.
Yeah, you're welcome.
Thank you. Would you say calculus is harder or?
God, it's been so long since I've taken calculus. I didn't find calculus. Well, I don't know. I didn't take a proof-based calculus course, so I can't speak to that. But like, I found calculus to be easier than organic chemistry, just because like what you're doing is more. Like in calculus, it's like it's been a long time. I probably couldn't do it now, but like like if you learn like integration by parts or like how to do derivatives and stuff like that, you have a formula, and it always math always works out really cleanly because it's math. It doesn't represent anything physically real. So there's like fundamental things there that always are true. Whereas in organic chemistry, and we see this in general chemistry too, it's like there is no first principles. So you'll have this, we'll teach you something. And then there's like 500 exceptions to it. And like, that's what makes it hard, I think, is there's so many exceptions, it gets really confusing. So it's a little less easy in that way.
Okay, thank you.
Yep.
You're a little tired today, John? Did you not get much sleep last night?
I am very tired today. Yeah, I did last night and the night before. I had my kid. He's getting his last molar in. So I'm hoping after that we sleep better. But yeah, I'm tired. I haven't eaten anything. So I'm just kind of a mess today. But
Right. Well, rest yourself. I'll see you another day.
Yeah, man. Good luck on studying with your exam.
Thank you. Appreciate it. Have a good day.